Hey everyone, we're going to move right into lesson 12 today, and we're going to start looking at systems of equations. And as we get into the lesson, I'll explain more in detail about what that means. But we're going to start off with 12.1 with milkshakes, where we have Diego and Lynn. And Lynn starts with 12 ounces and drinks a fourth of an ounce per second. Diego actually starts with 20 ounces and drinks 2/3 of an ounce per second. You're going to start off by thinking about how long it's going to take each of them to finish their milkshakes. Okay, I'm going to relate each of their information to an expression if we think about what's happening with Lynn. And this is an important piece, so if maybe you didn't create an expression, this would be an opportunity to write that down as we progress through this idea of systems of equations. So she starts with 12, and then she's drinking a fourth of an ounce per second. So we're going to say X is the number of seconds. Whereas Diego is going to be starting with 20 ounces and then drinking 2/3 of an ounce per second. And again, X is the number of seconds. So Lynn, to finish her milkshake, we would want to essentially think about each of these being set equal to 0 ounces, and it will take Lynn a total of 48 seconds, and it will take Diego a total of 30 seconds. So Diego will finish his milkshake first. If we think about not graphing these, but what the components of this would look like on a graph, I'm going to take you back to y equals mx plus b, where b is your starting point. So if I'm really thinking about what I set up earlier, each of these values represent the, that's a little confusing because that's the same color I used earlier. Let me grab green. Okay. Here and here represent that starting point, and then your slope is being represented by the rate of change at which is happening per second. So that's what it would kind of come together as on a graph. Okay, so moving on to 12.2. We have a couple of components. We have a nice big situation we're going to pick apart. We're going to create equations. We're going to graph, and then we're going to answer some follow-up questions. So these next two activities will take us into systems. They're going to both be different but relate to systems. All right, in this information that we have, there's a hiking trail, and I'm visual. I like to draw things out. It's near a town where Han and Jada live. It starts at a parking lot. So let's say this is my parking lot. And they walk a trail, and it ends at a lake. Here's my lake. And both of them decide to hike from the parking lot to the lake and back. So they're going there and back. But they are starting at different times. So at the time when Han reaches, let's say here's Han. By the time Han reaches the lake, Jada is 0.6 miles away from the parking lot. So let's just maybe say, let's say right here. And she is walking at a speed of 3.2 miles per hour towards the lake. Now, they give us some information about Han in terms of an equation. They say that his distance from the parking lot can be expressed as such, right here. So this represents Han. But we essentially want to think about what equation is going to represent Jada. So I'll give you a second to think about that. Okay, so what I know about Jada is that she's starting at 0.6 miles. That's essentially my y-intercept. Whoops, didn't want that. Here we go. That's essentially my y-intercept. And the speed at which she is walking is my slope. So if I'm going to stay consistent with the variables that are used here, so this is Han. I'm now making one for Jada. Jada is going to be d equals, let me start with the slope, 3.2 t plus the starting point, which is 0.6. Okay, so those are the two equations that represent both of their situations. So here we have, that's Jada. I don't like that it did that. Okay. And now we're going to move into graphing. And what I'm going to actually have you do before you kind of see what this looks like, I'm going to have you graph both of these, and you're going to go straight to number 3, and you're going to find where do these two graphs intersect each other. And that's what you're going to tell me. What are the coordinates of that point? So once you see what it looks like on the graph, you're going to type in what coordinate they intersect at. Okay, I'm going to do just a quick sketch of the graph. You should have graphed it by now. Let's see, try and make this as accurate as possible. Okay, let's see. That's a good amount of points. Okay, so right now that line, that's going to represent Han, because that starting point is at 4.8, which is right here. And then my other line will be here. Let's see, here, here, and I don't know, I think I'm about right here. Am I off a little bit? Hold on. 1 should be, yeah, like right there. Okay, I have enough points to connect. And now you'll see, this is, what was your name? Jada? Jada? Han and Jada. Yes, Jada. Okay, there we go. And, oh guys, I hope my sound's on. I haven't checked. Okay, so the point at which they intersect would be right here. And that would be 0.753 would be your ordered pair. So what does that mean? Well, first of all, we know that 0.75 is the hours, which is essentially 45 minutes. And it's 45 minutes after Han left the lake that he will pass Jada on the trail. So this happens at 3 miles from the parking lot. So 45 minutes after Han left the lake, he passed Jada. And then again, this happens at 3 miles from parking lot. So if you want, you can go back to my visual on the top. So you know, here, again, we said this was Jada. So by the time he turns around and they pass each other, it's 45 minutes and we're going to be at the 3 mile mark. Or not 3 mile mark, 3 miles from the parking lot. All right, let's see. What has to be true? Well, these values of T and D make Jada's equation true. And the values of T and D also make Han's equation true, really answering both of those. And so that's where that leads us into this idea of a system. A system meaning we have more than one equation. So we had up here on the top in blue and in the pink that I highlighted, we would call that a system. And often you'll see in your lesson summary that you sometimes note it with brackets. But it's basically saying I have two equations and I'm looking to see what solution is true for both of them. And in this case, we know that the solution is true when the time is 0.75 and the miles is 3. And so we would say that this is a system of equations. And I would also say the solution is 0.753. Or you could sometimes say like T is 0.75 and D is 3, whatever you want to do, but you have to identify that solution. Okay? Alrighty, so let's finish this up. The last problem is not as detailed. We go back to that idea of the stacked cups, and they actually give us the equations. So H is equal to this for a stack of small cups, and then for a stack of large cups, H is equal to this. And again, just remember, if you kind of think back to what the stacked cups look like. So if this is let's do a small one and a large one. If these are my small stacked cups, I know that this distance here is 6, and the top is 1.5 added for every cup, and then we have 9 and 1.5 added for every cup. So just a little bit of a visual for you guys to think about in terms of the large cups versus the small cups. Okay, so they want us to graph that. So go ahead and take a moment to graph. And it says make sure to label the axes and decide on the appropriate scale. So if you want to pause and do it, if you want to follow my steps, that's fine too. I'm not going to have you type anything for this one. But I'm going to go ahead and let my x-axis represent the number of cups. And then my y-axis is going to represent the height, the total height of the stack. And I'm going to go ahead and count by ones for my x-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And I'm going to go by 2s on the y-axis. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And I'm going to start with the small cups. I know I have to start with a y-intercept of, let me grab a color. We'll do pink for small. I have to start at 6, which is here. And then I'm basically increasing by 1.5 every time. So I'm going to just kind of estimate where that's going to fall. So around, whoopsies, here, somewhere close to here. Ish, around there. It's not going to be perfect because I'm kind of estimating 4 is going to actually be right at 12. Oh, that one didn't take. And somewhere around here. I have enough points that I'm going to connect. So that's for the small stack. Then my large stack will go blue for my large cup. Here we're going to start at 9. And again, I'm just going to kind of do my best job estimating the points on here. What am I at? 3. Somewhere around there. Okay. It's close enough. But let's talk about what we noticed. For what number of cups will the 2 stacks have the same height? Well, that's never going to happen. And the reason being, never will happen. The reason being is because they never intersect, right? The lines are parallel. If we go back to this second activity, where the lines intersect is your solution. These did not intersect, so this has no solution. And again, my system, if I want to write it out as a system, I would say that my system was h is equal to 1.5n plus 6, and h is equal to 1.5n plus 9, and there's no solution. So you could see this in your lesson summary. A system of equations is a set of two or more equations where the variables represent the same unknown values. They provide you an example, and they have that visual again. So you'll see here, this is what a system looks like. This is the solution to that system, because it's where the points intersect. And if they do not intersect, when the lines do not intersect, there is no solution. And those lines will always be parallel. When the lines intersect, there is one parallel. Now, we didn't see this, but when the lines are right on top of each other, there are infinitely many solutions. And let's just, for example, say I had a system that was y equals 2x plus 5 and y equals 2x plus 5. Well, if I graph both of these equations, they're the exact same line. They lie on top of each other. So we would say it's infinite solution. So pulling that piece back in there again. Okay? All right. So with that being said, oh, I don't have the homework in here again. So let's go with practice problems. I just lost my page. 1 second. Let's give, on page 67 to 68, we'll go with number 1 and 2. And let's just do 1, 2, 1, 2, 3. How about that? All right, good luck. Sorry this was extra long.